And the thing is, these two different measures have different biases. Let's look at some examples. Let's look, for example, at a case for the relative risk in which we have two diseases that have very little prevalence. Okay? So let's say that n is equal to 10 to the 7. We have 10 million patients. That is approximately what we have in our population. And we have disease P1. The prevalence of disease 1 is 10 to the 3. And the prevalence of disease 2 is 10 to the 2. So one disease affects 1,000 patients and the other one affects 100 patients. In that case, the relative risk reduces to C12 times 10 to the 7 divided by 10 to the 3 times 10 to the 2, and this is a 5 there, so we have C12 times 10 to the 2. So in that case, the relative risk of observing even one patient affected by both diseases is 100. It takes really high values because it is biased because of the fact that these two diseases are very little prevalent. So the probability that you expect at random of seeing these two diseases affecting a same person is very low. It's smaller than 1 actually. And that biases the relative risk to take high values. Now what happens if we would have two diseases that are highly prevalent? Okay? So, and the question that we're going to make here is, when we have two diseases that are highly prevalent, what is the maximum value that the relative risk can take? So we're going to use similar example with, again, 10 million patients, but we're going to look at a disease that is affecting half of the population, and another disease that is affected 1/4 of the population. Okay? So we have two highly prevalent diseases, one that affects 50%, the other one affects 25% of the population. And we wonder, what is the biggest value that the relative risk can take in that case? What is the upper bound? The upper bound we can obtain when all the patients affected by disease 2 also have disease 1. There's complete overlap. So in that case, C12 is also equal to P2. In that case, then, the relative risk when C12 is equal to P2 is n divided by P1. That is the maximum value, and the maximum value, n divided by P1, in this case is 10 to the 7, 5 times 10 to the 6, this is equal to 2. So the maximum value that the relative risk could take when you have like these very highly prevalent diseases is a value of 2. So when you look at the numbers that the relative risk gives you, it's going to be biased to be high for diseases that have little prevalence, and it's going to be biased to be low for diseases of low prevalence.